Two galaxies are colliding right now, and not a single star will hit another star. That's how empty galaxies really are. What looks like cosmic carnage is actually billions of stars passing through each other like ghosts. This emptiness isn't just a curiosity, it's the reason you're alive. If you're curious about the universe, please subscribe to the channel. It helps us continue bringing you the latest discoveries from the edge of space and time. Now let's get started. Let's start with something tangible. Imagine you're holding a grain of sand between your fingers. That tiny speck represents our sun. Now, where would you place the next grain of sand to represent the nearest star, Proxima Centauri? You'd have to walk about 8 kilometers away. 8 kilometers of completely empty space between two grains of sand. This is the reality of stellar distances, and it's not just around our sun. This emptiness is standard throughout the Milky Way and every other galaxy in the universe. The Milky Way contains somewhere between 200 billion and 400 billion stars, depending on which recent census you trust. The latest data from the Gaia Space Telescope, particularly its third data release from 2023, has given us unprecedented precision in mapping stellar distances. We now know that our galaxy stretches roughly 100,000 light-years across its main disk. Recent studies published in 2024 in Nature Astronomy revealed something fascinating. The Milky Way doesn't have the simple structure we thought it did. Instead of a smooth exponential decline in star density as you move outward, there's actually a broken profile with an almost flat distribution of stars between 3,500 and 7,500 parsecs from the galactic center. But here's where the emptiness becomes staggering. When astronomers measured the half-light radius of the Milky Way, essentially where half of all the starlight comes from, they found it at 5.75 kiloparsecs, or about 18,700 light-years from the center. This measurement, published by an international team led by researchers at Yunnan University, shows our galaxy is actually larger than we previously thought. Yet even with this larger size and all those hundreds of billions of stars, the actual matter occupies less than a trillionth of the galaxy's total volume. Think about that for a moment. If you could somehow freeze the Milky Way in time and examine every cubic meter of space within it, you'd find that almost all of those cubic meters contain absolutely nothing. No stars, no planets, no asteroids, just the faint whisper of occasional atoms drifting through the interstellar medium. The average density of matter in our galaxy is so low that it makes the best vacuum we can create in laboratories on Earth look crowded by comparison. Why does this matter? Because this emptiness isn't a bug in the cosmic design, it's a feature. The vast spaces between stars are precisely what allow galaxies to exist as stable structures over billions of years. If stars were packed closer together, their gravitational interactions would be catastrophic. Stellar encounters would be common, flinging planets out of their orbits and disrupting solar systems constantly. The emptiness is what gives us stability. To truly grasp the scale, we need to understand what astronomers mean when they talk about distance in space. When we say the nearest star to us, Proxima Centauri, is 4.24 light-years away, we're saying that light, traveling at nearly 300,000 kilometers per second, takes 4 years and about 3 months to cross that gap. In more familiar units, that's roughly 40 trillion kilometers. The fastest spacecraft humans have ever built, Voyager 1, would take about 75,000 years to reach Proxima Centauri if it were headed in that direction, which it isn't. The European Space Agency's Gaia mission has been measuring the distances to stars with unprecedented accuracy using a technique called parallax. By observing how nearby stars appear to shift position against more distant background stars as Earth orbits the Sun, Gaia has created the most detailed three-dimensional map of our galaxy ever made. The latest data release includes precise measurements for over 1.8 billion stars. Yet even with all these measurements, we're only mapping a tiny fraction of the Milky Way's stars, and every single one of them is separated from its neighbors by unimaginable gulfs of space. Here's something that might surprise you. The density of stars actually changes depending on where you are in the galaxy. Near the galactic center, stars are packed more tightly together. In the central bulge of the Milky Way, the average distance between stars might be just 1 light-year, or even less. But even there, in the most crowded stellar neighborhood in our galaxy, the space between stars is still enormous compared to the sizes of the stars themselves. Our Sun has a diameter of about 1.4 million kilometers. If you could line up suns between here and Proxima Centauri, you'd need about 28 billion of them. Out in the spiral arms where we live, about 26,000 light-years from the galactic center, the stellar density is much lower. Recent research published in the Astrophysical Journal in 2024 used data from the Apogee survey, which is part of the Sloan Digital Sky survey, to map the structure of the Milky Way out to distances of 10,000 parsecs, or about 32,600 light-years. They found that in our neighborhood, the typical distance between stars is about 5 light-years, though this varies considerably. Some regions are more crowded, others even more sparse. If you're fascinated by the vast emptiness of space and how it affects long-term space travel, you might want to check out my video called The Terrifying Reality of Generation Ships, where we explore what it would actually mean for humans to cross these enormous interstellar distances. The challenges are more profound than you might imagine. The link is in the description. The emptiness extends beyond just the spaces between stars. Between the spiral arms of our galaxy, there are even larger voids where star density drops even further. The Milky Way has several major spiral arms: the Perseus arm, the Scutum Centaurus arm, and the Sagittarius arm, among others. Between these arms lie what astronomers call inter-arm regions, where star formation has been less active and the stellar population is thinner. Recent three-dimensional mapping published in Astronomy and Astrophysics in 2024 identified what might be a large underdensity, possibly corresponding to an inter-arm gap, in the direction toward the galactic center. But stars aren't the only things in galaxies. There's also gas and dust, the raw materials from which new stars form. The interstellar medium, as it's called, fills the space between stars with a thin haze of hydrogen, helium, and trace amounts of heavier elements, along with tiny dust grains. Yet even this material is extraordinarily diffuse. In the densest molecular clouds where stars are actively forming, the density might reach 10 million atoms per cubic centimeter. That sounds like a lot until you realize that the air you're breathing right now contains about 25 quintillion molecules per cubic centimeter. The densest regions of star-forming clouds in space are still a better vacuum than anything we can achieve in terrestrial laboratories. A comprehensive three-dimensional dust map of the Milky Way published in 2024 used data from over 120 million stars observed by Gaia, 2MASS, and all WISE. This map extends out to 2.8 kiloparsecs, about 9,000 light-years, and reveals the intricate structure of dust throughout our local region of the galaxy. Even in regions where dust appears thick when viewed through telescopes, creating dark lanes across the Milky Way's bright band, the actual density of material is astonishingly low. If you were floating in one of these thick dust clouds, you probably wouldn't even notice. The dust particles are separated by meters or even kilometers, invisible to your eyes unless you had instruments sensitive enough to detect individual grains. Part of what makes galaxies so empty is that stars themselves are tiny compared to the distances between them. Our Sun, which is a fairly average star, has a radius of about 700,000 kilometers. That seems enormous. It's more than 100 times the diameter of Earth. But space is so vast that even this immense ball of plasma becomes microscopic when compared to interstellar distances. The ratio of a star's size to the distance between stars is roughly similar to the ratio between a marble and the distance from New York to Los Angeles. The Milky Way's structure becomes even more interesting when you consider its vertical thickness. The disk of our galaxy, where most stars reside, has a scale height of only about 300 parsecs, or roughly 1,000 light-years, in our neighborhood. This means the galaxy is extremely flat relative to its diameter. If you made a scale model of the Milky Way the size of a coin, say 2.5 centimeters across, the disk would be thinner than a sheet of paper. Yet even within this relatively thin disk, the emptiness dominates. When you venture beyond the main disk into what's called the galactic halo, the emptiness becomes even more extreme. The halo surrounds the disk in a roughly spherical distribution and contains old stars, globular clusters, and large amounts of mysterious dark matter. Stars in the halo are so widely separated that calling them isolated would be an understatement. Some halo stars orbit the galaxy on paths that take them tens of thousands of light-years above or below the galactic plane, traveling through regions where the nearest neighbor might be dozens of light-years away. Understanding this emptiness helps us appreciate why interstellar travel is so challenging. Science fiction often depicts space travel as journeying through a crowded cosmos where you might encounter another star system just by flying in a straight line for a while. The reality is that hitting another star system by accident would be like throwing a grain of sand in New York and having it accidentally strike another specific grain of sand somewhere in California. The precision required is almost unimaginable. This vast emptiness also explains why collisions between stars are incredibly rare. Even when two galaxies collide, and we'll explore this more deeply later in this script, the actual stars almost never hit each other. The galaxies pass through one another like two clouds of smoke interpenetrating, with the individual stars threading the needle through vast empty spaces. Computer simulations of galactic collisions show that while the overall structure of both galaxies gets dramatically disrupted by gravitational forces, the probability of any two stars actually colliding is vanishingly small. Recent observations from the James Webb Space Telescope have given us breathtaking views of distant galaxies, some seen as they appeared more than 13 billion years ago, when the universe was still young. Even these ancient galaxies, formed in the denser conditions of the early universe, show the same fundamental character: brilliant points of light separated by enormous voids. The emptiness of galaxies isn't just a feature of our modern universe, it's been a characteristic of cosmic structure since the first galaxies assembled from primordial gas clouds in the wake of the Big Bang. The distribution of stars within galaxies follows patterns that astronomers have studied extensively. In spiral galaxies like the Milky Way, star density decreases roughly exponentially as you move outward from the center. Though, as we mentioned earlier, recent research shows this isn't a simple exponential, but has a more complex broken structure. In elliptical galaxies which lack the disk and spiral arms, the distribution is different but equally dominated by empty space. No matter what type of galaxy you examine, the overwhelming reality is that stars occupy only an infinitesimal fraction of the galaxy's volume. The question naturally arises, if galaxies are so empty, why do they look so crowded in photographs? This is where understanding light and perception becomes crucial. When you see a photograph of the Milky Way or another galaxy, you're seeing the cumulative light from billions of stars integrated along your line of sight. Every photon that reaches the camera has traveled across vast stretches of emptiness, but the camera doesn't capture the emptiness, it only captures the light. It's similar to looking at a city from an airplane at night. The lights appear to form a continuous glow, but you know that between each streetlight, each house, each building, there are spaces, roads, parks, and empty lots. The darkness doesn't show up in the photograph the same way the lights do. Professional astronomical images often enhance this effect. Most galaxy photographs you see online or in books are long exposure images, sometimes combining hundreds of separate exposures, each lasting minutes or even hours. During this time, the camera accumulates photons from even the faintest stars, building up an image that shows far more detail than your eye could ever see, looking through the same telescope. These images are then often processed to increase contrast, bringing out subtle structures in the galaxy's spiral arms or highlighting regions of active star formation. The result is visually stunning, but it can be misleading about the actual nature of galaxies as mostly empty space with occasional islands of matter. There's also a selection bias in what we photograph. Astronomers and astrophotographers naturally point their instruments at the most interesting and photogenic targets, bright star clusters, glowing nebulae, the dense central regions of galaxies where light is most concentrated. You rarely see publications featuring photographs of the empty spaces between spiral arms or the vast voids between stars because there's nothing visible there to photograph. It's like how nature documentaries show you exciting wildlife behavior but rarely show the hours of waiting in between events. Let's explore the mathematics of galactic emptiness more rigorously. If we consider a typical region of the Milky Way's disk near the Sun, we can calculate the actual volume occupied by stars versus the total volume of space. Within a sphere with a radius of 10 parsecs, about 32.6 light-years, centered on the Sun, there are approximately 20 stars based on our current census. Each of these stars has a volume determined by its radius. For simplicity, let's assume they're all similar to the Sun, though in reality they range from tiny red dwarfs to larger giants. The Sun's volume is about 1.4 million billion cubic meters. Multiply that by 20 stars and you get the total volume occupied by stellar material in this region. Now compare that to the volume of the sphere itself. A radius of 10 parsecs is about 300 billion meters, and the volume of a sphere is 4/3 pi times radius cubed. When you do the calculation, you find that stars occupy roughly 1 trillionth of the volume. Put another way, 99.9999999% of the space is empty, and that's in a relatively crowded part of the galaxy. The emptiness becomes even more profound when you consider that much of what we call empty space isn't truly empty in the quantum mechanical sense. The vacuum of space seethes with virtual particles constantly appearing and disappearing, borrowing energy from the quantum field for infinitesimally brief moments before annihilating back into nothingness. The cosmological constant, or dark energy, fills even the most remote voids with a mysterious presence that's driving the accelerating expansion of the universe. So in a philosophical sense, even the emptiest regions of galaxies contain something, though that something is far stranger than ordinary matter. This brings us to another crucial component of galaxies that fills the space between stars: dark matter. Although we cannot see dark matter directly, its gravitational effects are unmistakable. The rotation curves of galaxies, measurements of how far stars orbit at different distances from the galactic center, reveal that visible matter alone cannot account for the observed motions. There must be additional mass, roughly 5 times more than all the visible stars and gas combined, distributed throughout galaxies in enormous halos. Recent work published in Astronomy and Astrophysics in October 2023 detected what's called the Keplerian decline in the Milky Way's rotation curve using Gaia data. This is the region at the galaxy's outskirts where orbital velocities begin to decrease, indicating you're reaching the edge of the galaxy's mass distribution. The team found that velocity decreases by approximately 30 kilometers per second between 19.5 and 26.5 kiloparsecs from the galactic center. This decline helps astronomers map where the dark matter halo extends and how it's distributed. Dark matter pervades the space between stars, passing through ordinary matter as if it weren't there. Right now, as you watch this video, countless dark matter particles are streaming through your body, through the Earth, through everything, without interaction. The density of dark matter in our solar neighborhood is estimated at roughly 0.3 protons per cubic centimeter, which sounds like almost nothing, and it is. But integrated over the entire galaxy, this diffuse presence adds up to more mass than all the stars combined. The space between stars isn't quite as empty as it appears. It's filled with an invisible presence that we've only begun to understand. Another way to appreciate galactic emptiness is to consider what would happen if you randomly teleported to a location somewhere within the Milky Way. What would you see? The odds are overwhelming that you'd find yourself in intergalactic space with no stars visible to the naked eye nearby. You'd be floating in darkness with the distant glow of the galactic disk perhaps visible far away if you were in the halo, or you might be deep in a void between spiral arms where even that glow is dim. The chances of appearing near a star, close enough to see it as more than just a point of light, are astronomically small, literally. Let's quantify this. The volume of the Milky Way's disk, approximating it as a cylinder with a radius of 50,000 light-years and a thickness of 2,000 light-years, is roughly 8 billion cubic light-years. If the galaxy contains 300 billion stars and each star's territory extends about 2 light-years in radius, that's a sphere of about 33 cubic light-years per star. Multiply 300 billion stars by 33 cubic light-years each, and you get about 10 trillion cubic light-years of stellar neighborhoods. Divide that by the total volume of 8 billion cubic light-years, and you find that stellar neighborhoods occupy more than 100% of the galaxy's volume. Wait, that can't be right, can it? This apparent paradox reveals something interesting. Stellar neighborhoods overlap. The spheres of influence around stars are not discrete territories with hard boundaries. Instead, gravitational influence extends in principle to infinity, though it weakens with distance. What this calculation really shows is that you're essentially always in some star's gravitational field, however weakly, but the vast majority of the galaxy's volume is far enough from any star that its influence is negligible. If we instead ask what fraction of the galaxy's volume is within, say, 1 light-year of a star, close enough that the star would appear distinctly brighter than others in the sky, the calculation changes dramatically. A sphere with a 1 light-year radius has a volume of about 4 cubic light-years. With 300 billion stars, that's 1.2 trillion cubic light-years of close to a star space. Divide by the galaxy's total volume of 8 billion cubic light-years, and you get about 150. This still seems wrong because we're using a simplified cylindrical model of the galaxy, which underestimates its total volume when you include the halo and the regions between spiral arms. Let's use a more realistic model. If we consider the Milky Way's total volume including its dark matter halo, which extends perhaps 300,000 light-years from the center in a roughly spherical distribution, the volume becomes truly enormous, about 113 quadrillion cubic light-years. Now, when you calculate what fraction is within 1 light-year of a star, you get about 1%. That means 99% of the Milky Way's total volume is more than 1 light-year from the nearest star, a distance at which that star would appear only slightly brighter than the other points of light in the sky. This emptiness has profound implications for the future of space exploration. When we dream of traveling to other stars, we're contemplating journeys across these vast voids. The nearest potentially habitable planet we know of, Proxima Centauri b, orbits our nearest stellar neighbor at that distance of 4.24 light-years. With current technology, reaching it would take tens of thousands of years. Even with hypothetical future technologies like fusion rockets or antimatter drives, the journey would likely take decades or centuries. The emptiness of space isn't just a curious fact, It's a fundamental barrier to exploring our cosmic neighborhood. Yet this same emptiness may be what makes complex life possible. If stars were packed closer together, the night sky would never be dark. Multiple suns would illuminate planets from different angles, creating complex patterns of light and shadow, making stable climates more difficult. The radiation environment would be harsher, with stellar flares and supernovae from nearby stars posing constant threats. The gravitational perturbations from passing stars would disrupt the orbits of planets and comets, potentially sending extinction-level impactors toward inhabited worlds on a regular basis. Our own solar system has remained relatively stable for over 4.5 billion years, giving life time to evolve from simple single-celled organisms to the complex biosphere we see today, including us. This stability is possible largely because we're isolated in a quiet region of the galaxy, far from the crowded and chaotic galactic center, with no close stellar neighbors to disturb our orbital dynamics. The emptiness that makes space travel difficult is the same emptiness that made our existence possible. There's also a temporal dimension to galactic emptiness. Stars don't remain fixed in their positions. They orbit the galactic center on paths that can take hundreds of millions of years to complete. Our Sun, for example, takes approximately 225 million years to orbit once around the Milky Way, a period sometimes called a galactic year. During this orbit, we pass through different regions of the galaxy, sometimes traveling through spiral arms where star density is higher, sometimes traversing the quieter inter-arm regions. These passages may have influenced Earth's history. Some researchers have proposed correlations between our spiral arm crossings and ice ages or mass extinctions, though this remains controversial. As stars orbit, the specific configuration of which star is nearest to which other star slowly changes. 4.24 light-years is the current distance to our nearest neighbor, but this hasn't always been the case. Computer simulations tracking stellar motions backward and forward in time suggest that roughly 1.3 million years ago, a red dwarf star called Schultz's star passed within about 0.8 light-years of the Sun, roughly 1/5 the current distance to Proxima Centauri. Even at this closer approach, Schultz's star would have appeared only as a bright point in Earth's sky, visible but not dramatically different from other bright stars. The emptiness persists even during these rare close encounters. Looking forward, simulations predict that in roughly 1.3 million years from now, Gliese 710 will pass within 1.1 light-years of the Sun. Again, even this relatively close approach maintains the fundamental emptiness of space. True stellar collisions, where two stars actually impact each other, are so rare in the galactic disk that they may have never occurred during the entire history of the Milky Way among the general stellar population. They're only common in the extremely dense cores of globular clusters, ancient collections of hundreds of thousands of stars packed into regions just tens of light-years across. Now let's turn our attention to what actually exists in the seemingly empty space between stars. While we've established that galaxies are overwhelmingly vacant, the voids aren't completely devoid of matter. The interstellar medium, that thin soup of gas and dust permeating the space between stars, plays a crucial role in the galactic ecosystem. Without it, no new stars could form, and galaxies would gradually fade as their existing stars exhausted their fuel and died. The interstellar medium comes in various forms, each with different temperatures, densities, and compositions. The coldest and densest regions are molecular clouds, where temperatures drop to just 10 or 20 degrees above absolute zero. In these frigid environments, hydrogen atoms pair up to form molecular hydrogen, and trace amounts of other molecules appear: carbon monoxide, water, ammonia, and even complex organic compounds. These molecular clouds are the stellar nurseries of the galaxy, the places where gravity can overcome the thermal pressure of gas and compress material into new stars. Even in these densest regions, the emptiness remains striking. A typical giant molecular cloud might contain enough mass to form 10,000 or even 100,000 new stars, yet spread that mass across a region 100 light-years across, and the density remains incredibly low. If you were floating inside a molecular cloud, you wouldn't see thick fog or darkness surrounding you. You'd see essentially nothing with your naked eye. Only with sensitive instruments could you detect the presence of molecules around you, spaced meters or kilometers apart. The Apogee survey and other spectroscopic studies have mapped the distribution of molecular gas throughout the Milky Way. A comprehensive catalogue published in Astronomy and Astrophysics in December 2024 identified large molecular clouds across the galactic plane, creating a three-dimensional structure extending out to 10 kiloparsecs from the Sun. These clouds trace the spiral arms of the galaxy, revealing how star formation concentrates in certain regions, while leaving vast expanses relatively empty of both stars and the gas that makes them. Between the molecular clouds lie warmer regions of atomic hydrogen. Here, temperatures rise to thousands of degrees, and hydrogen exists as individual atoms rather than molecules. This warm neutral medium fills much of the volume of the galactic disk, though again with extremely low density, typically around 0.1 to 1 atom per cubic centimeter. For comparison, the best vacuum chambers on Earth achieve densities around 1,000 to 1 million molecules per cubic centimeter. Interstellar space naturally achieves vacuum conditions billions of times better than our best technology. Then there are regions of ionized hydrogen where ultraviolet radiation from hot young stars strips electrons from atoms, creating glowing nebulae. These are among the most beautiful objects in the galaxy, gorgeous clouds painted in shades of red, pink, and blue. The Orion Nebula, visible to the naked eye as a fuzzy patch in Orion's sword, is one such region. Yet even these apparently thick clouds have densities of only a few thousand atoms per cubic centimeter in their densest parts. Most of their volume contains far less. The nebula glows brightly not because it contains much matter, but because the matter present is energized by intense stellar radiation. The hottest component of the interstellar medium is the coronal gas, heated to millions of degrees by supernova explosions and stellar winds from massive stars. This gas is so diffuse, with densities as low as 0.001 atoms per cubic centimeter, that it's essentially invisible except through X-ray observations. NASA's Chandra X-ray Observatory and the European Space Agency's XMM Newton satellite have mapped this hot gas throughout the galaxy, revealing a complex structure of bubbles and filaments carved by stellar violence. Supernovae explosions blast cavities in the interstellar medium, creating shells of hot expanding gas that can persist for millions of years. Our own Sun sits within one such bubble, called the local bubble, a region roughly 1,000 light-years across, where the density of interstellar material is even lower than average. This bubble was likely created by multiple supernova explosions that occurred in our neighborhood within the past 10 to 20 million years, sweeping gas and dust away and leaving behind a cavity. Recent three-dimensional dust mapping studies using Gaia data have revealed the structure of the local bubble in unprecedented detail, showing how our solar system moves through this underdense region as we orbit the galaxy. Dust grains, though far less abundant than gas, play an outsized role in galactic processes. These microscopic particles, typically less than a micrometer across, form in the atmospheres of cool, evolved stars and in supernova ejecta. Each grain is a tiny conglomeration of carbon, silicon, oxygen, iron, and other heavy elements forged in stellar furnaces. In aggregate, dust makes up only about 1% of the mass of the interstellar medium, yet it absorbs and scatters starlight profoundly, creating the dark lanes you see cutting across the Milky Way in photographs. The three-dimensional dust mapping project published in May 2024 used photometry from 120 million stars to map dust density throughout our local region of the galaxy with unprecedented resolution. The maps reveal a complex structure with dense filaments, sheets, and clouds interspersed with clearer regions. Yet even in the densest dust lanes where extinction dims starlight significantly, the actual number of dust grains per cubic meter might be only a few dozen or a few hundred. The grains are separated by meters or tens of meters, vast distances compared to their micrometer sizes. Dust serves crucial functions in the galactic ecosystem. It shields molecular clouds from destructive ultraviolet radiation, allowing molecules to form and persist. It provides surfaces where chemical reactions can occur, including the formation of molecular hydrogen itself, which is difficult to form in gas phase. Dust grains carry heat away from collapsing gas clouds, allowing them to contract under gravity. Without dust, star formation would be far less efficient, and galaxies might look very different than they do. Cosmic rays, high-energy particles accelerated to nearly the speed of light, also fill the space between stars. These particles, mostly protons with some heavier nuclei and electrons, have been accelerated by supernova shock waves and other violent processes. They stream through the galaxy, bouncing off magnetic fields in a process called diffusion. Right now, cosmic ray particles are constantly striking Earth's atmosphere, creating showers of secondary particles that reach the surface. Some of these particles are passing through you as you watch this video, most without interaction, though occasionally one leaves a tiny track of damage in your DNA, usually repaired, but sometimes contributing to mutations. The energy density of cosmic rays in the galaxy is roughly comparable to the energy density of starlight, the energy density of the interstellar magnetic field, and the thermal energy of the gas. This rough equipartition of energy among different components suggests that galaxies exist in a kind of pressure balance, with different forms of energy and matter influencing each other. The cosmic ray pressure can even affect how gas collapses to form stars, slightly inflating molecular clouds and reducing star formation efficiency. Magnetic fields thread through the interstellar medium, organized on large scales into patterns that follow the spiral arms and connect to the galaxy's overall structure. These fields are extraordinarily weak by terrestrial standards, typically just a few microgauss, roughly 100,000 times weaker than Earth's magnetic field at its surface. Yet integrated over the vast volumes of space in galaxies, these weak fields contain enormous total energy and play important roles in controlling how gas moves and how cosmic rays propagate. The Planck satellite, which mapped the cosmic microwave background, also observed polarized emission from interstellar dust grains aligned by magnetic fields. These observations revealed the magnetic structure of nearby molecular clouds in exquisite detail. The fields show complex geometries with regions of order and chaos, reflecting the turbulent nature of the interstellar medium. Gas and fields interact in complicated ways, with magnetic tension resisting compression in some cases, while magnetic field lines can collapse along with gas in others, influencing where and how stars form. Neutrinos, those ghostly, nearly massless particles, also fill the space between stars. Produced in vast numbers by nuclear reactions in stellar cores, neutrinos travel at nearly the speed of light and almost never interact with anything. The Sun produces about 2 × 10⁻38 neutrinos every second. Most of these pass through Earth without interacting with a single atom. The neutrino density in our solar neighborhood from the Sun alone is about 10 billion per square centimeter per second, yet these particles are so non-interactive that they might as well not be there for most purposes. Still, they're part of what fills the empty space. Then there's the interstellar radiation field, the photons streaming through space from all the stars in the galaxy. These photons, spanning the spectrum from radio waves to gamma rays, with most energy in the optical and infrared bands, create a diffuse glow throughout the galaxy. If you were floating in interstellar space far from any star, you wouldn't be in complete darkness. The combined starlight from billions of distant suns would create a faint illumination, perhaps comparable to the light from a few dozen stars visible in Earth's night sky. It wouldn't be enough to read by, but it would be detectable to dark, adapted eyes. Space-based observatories have measured this diffuse background light carefully. The Cosmic Background Explorer and later missions found that the integrated starlight creates a background roughly equivalent to 1 photon per cubic centimeter in the optical and near-infrared bands. This radiation field interacts with dust, heating the grains and causing them to re-radiate energy in the infrared. It ionizes atoms in the diffuse gas, maintaining a low level of ionization even far from hot stars. The radiation field is part of the complex web of interactions that make the interstellar medium a dynamic, evolving system rather than a static emptiness. Gravitational waves, ripples in spacetime itself produced by accelerating massive objects, also propagate through the galaxy. Every binary star system, every neutron star merger, every black hole collision sends gravitational waves spreading outward at the speed of light. These waves are unimaginably weak by the time they reach us. The first detection by LIGO in 2015 measured a strain of less than 1 part in 10 to the 21st. Yet they're there, continuously washing over the galaxy, literally stretching and squeezing space itself by infinitesimal amounts as they pass. Dark matter, which we mentioned briefly before, deserves deeper examination. This mysterious substance, which doesn't emit, absorb, or reflect light, reveals itself only through gravitational effects. The latest rotation curve measurements from Gaia show that the Milky Way contains roughly 1 trillion solar masses of total matter, of which only about 200 billion solar masses is visible in stars, gas, and dust. The remaining 800 billion or so solar masses must be dark matter, distributed in an extended halo surrounding the visible galaxy. What is dark matter made of? We honestly don't know, and this is one of the most profound mysteries in modern physics. The leading candidate is some type of weakly interacting massive particle, or WIMP, perhaps left over from the Big Bang. Multiple experiments around the world are attempting to detect these particles directly, using ultra-sensitive detectors deep underground to shield them from cosmic rays. So far, no conclusive detections have been made, though the search continues. Alternative theories propose that dark matter might be primordial black holes, or that perhaps our understanding of gravity needs modification instead. The truth remains elusive. What we do know is that dark matter shaped the universe. In the early cosmos, after the Big Bang but before stars formed, dark matter began to clump under gravity. Its gravitational pull drew ordinary matter into these concentrations, eventually forming the first galaxies. Computer simulations show that without dark matter, the universe would look completely different. Galaxies either wouldn't form at all, or would be much smaller and less stable. The emptiness of galaxies exists within a framework created by invisible dark matter scaffolding. Recent studies using gravitational lensing, where the gravity of foreground mass bends and magnifies light from background objects, have mapped the distribution of dark matter in and around galaxies with increasing precision. These maps reveal that dark matter halos are roughly spherical and extend far beyond the visible stellar disk, sometimes 5 or 10 times farther than the most distant observable stars. The Milky Way's dark matter halo probably extends 200,000 light-years or more from the galactic center, though the density drops with distance. Throughout this enormous volume, dark matter particles outnumber ordinary matter particles roughly 5 to 1, yet both remain so diffuse that the emptiness still dominates. Understanding why galaxies are so empty requires us to look back in time, to the very beginning of cosmic history. The story starts 13.8 billion years ago with the Big Bang. when the universe erupted into existence from a state of unimaginable density and temperature. In those first moments, the universe was anything but empty. Matter and energy were compressed into a volume far smaller than an atom, with densities beyond comprehension. Yet within the first second, the universe expanded and cooled dramatically, setting in motion the processes that would eventually create the emptiness we observe in galaxies today. During the first 3 minutes after the Big Bang, nuclear reactions forged the lightest elements, hydrogen, helium, and trace amounts of lithium and beryllium. When these reactions ceased, the universe consisted of roughly 75% hydrogen and 25% helium by mass, along with the invisible dark matter. This primordial gas was nearly uniform, spread almost evenly throughout space, but not quite evenly. Tiny quantum fluctuations from the inflationary epoch, the brief period of exponential expansion in the universe's first fraction of a second, had imprinted subtle density variations, regions that were slightly more or less dense than average. These tiny variations, only about 1 part in 100,000, were the seeds of all cosmic structure. Regions that were slightly denser had slightly stronger gravity, attracting more matter. As they accumulated more matter, their gravity strengthened further, attracting even more material. This process of gravitational instability, first understood by the British physicist James Jeans in the early 20th century, drove the formation of structure in the universe. But this process works slowly. Without dark matter, it would have taken far too long for galaxies to form. The universe is only 13.8 billion years old, yet we see fully formed galaxies when the universe was only a few 100 million years old. Dark matter made galaxy formation possible on the timescales we observe. Because dark matter doesn't interact with radiation, it could begin clumping immediately after the Big Bang, while ordinary matter remained coupled to photons for the first 380,000 years. By the time ordinary matter finally decoupled from radiation, an event we observe as the cosmic microwave background, dark matter had already created significant concentrations of mass. Ordinary matter fell into these dark matter potential wells, collecting in regions where dark matter had already aggregated. The James Webb Space Telescope has revolutionized our understanding of early galaxy formation. Images released in 2022 and 2023 revealed galaxies as they appeared when the universe was only 200 to 400 million years old. These ancient galaxies appear surprisingly mature, with structures and stellar populations that suggest rapid formation. Some of these early galaxies are actually more compact than expected, with stars packed more densely than in modern galaxies, though still separated by vast distances relative to their sizes. Understanding exactly how these first galaxies assembled remains an active area of research. As gas collapsed into the first dark matter halos, it heated up. Gravitational potential energy converted into thermal energy, raising temperatures to thousands or even millions of degrees. Hot gas radiates energy away through atomic transitions, cooling over time. As the gas cooled, it could collapse further, concentrating into denser regions. But this process is self-limiting. Once densities rise high enough and temperatures drop low enough, gravitational instability fragments the gas into smaller clumps that collapse to form individual stars. The spacing between these clumps determines the eventual spacing between stars. Several physical processes determine this spacing. The gene's length, a fundamental scale in astrophysics, represents the minimum size a region must have for self-gravity to overcome thermal pressure. In the cold molecular clouds where stars form today, this length is typically a fraction of a light year, roughly the separation we observe between stars in clusters. But stars don't remain where they form. Born in groups and clusters, they interact gravitationally, some gaining energy and moving to wider orbits, others losing energy and sinking toward the center. Over millions of years, stellar clusters disperse, spreading their member stars throughout the galaxy. This dispersal process contributes to the emptiness of galaxies. If all stars remained in the compact clusters where they formed, galaxies would have a very different structure, with dense knots of stars embedded in even more empty space. Instead, the gravitational interactions within clusters and the tidal forces from the galaxy as a whole gradually dissolve most clusters, leaving only the most massive and tightly bound ones intact. The stars from dissolved clusters spread throughout the galactic disk, increasing the average separation between neighbors. The Milky Way contains about 150 globular clusters, ancient collections of stars that formed early in the galaxy's history. These clusters are remarkably dense by galactic standards, with stellar densities in their cores reaching 100 or even 1,000 stars per cubic light-year, compared to about 0.1 stars per cubic light-year in our solar neighborhood. Yet even in globular cluster cores, stars remain separated by light weeks or light months. A planet in such an environment would have a spectacular night sky filled with thousands of bright stars, yet the space between those stars would still be overwhelmingly empty. Computer simulations of galaxy formation have become increasingly sophisticated, incorporating dark matter dynamics, gas physics, star formation, stellar feedback, and numerous other processes. These simulations begin with the initial conditions from the Big Bang and evolve forward in time, following the collapse of dark matter and gas into galaxies. Modern simulations like the illustrious TNG project or the Eagle simulations can reproduce many observed properties of galaxies, including their sizes, shapes, stellar masses, and distributions. These simulations reveal that the emptiness of galaxies is almost inevitable given the physics of structure formation. When gas collapses under gravity, it doesn't fall into a single point. Instead, conservation of angular momentum causes it to form a rotating disk. Within this disk, the specific processes of star formation, which convert only a small fraction of the gas into stars at any given time, naturally produce widely separated stellar systems. The turbulence in the interstellar medium, driven by stellar feedback, creates a complex structure of dense filaments and clumps embedded in lower density surroundings. Stellar feedback, the energy and momentum that stars inject back into their surroundings, plays a crucial role in maintaining galactic emptiness. When massive stars explode as supernovae, they release enormous energy, roughly 10 to the 44 joules in a single explosion. This energy blasts cavities in the interstellar medium, sweeping gas into shells and creating regions of very low density. Multiple supernovae in the same region can create superbubbles, cavities hundreds of light-years across, where gas density drops even below the already low galactic average. Stellar winds from massive stars, radiation pressure from hot young stars, and outflows from supermassive black holes at galactic centers all contribute to this feedback. These processes heat gas, blow it away from star-forming regions, and in extreme cases can drive galactic-scale winds that eject material entirely from the galaxy into the surrounding intergalactic space. Feedback is self-regulating. Vigorous star formation produces strong feedback that suppresses further star formation, preventing gas from converting too efficiently into stars. Without this regulation, galaxies would have converted all their gas into stars long ago, leaving no material for ongoing star formation. The efficiency of star formation is surprisingly low. In molecular clouds today, only about 1 to 10% of the gas mass actually ends up in stars. The rest is dispersed by feedback before it can collapse. This low efficiency is part of why galaxies retain so much empty space. If star formation were more efficient, galaxies would be denser, with stars packed more closely together. The balance between gravity trying to compress gas into stars and feedback trying to disperse it determines the overall structure of galaxies and contributes fundamentally to their emptiness. Galaxy mergers and interactions also shape the distribution of stars and the amount of empty space. When two galaxies collide, their dark matter halos and stellar components pass through each other like ghosts, as we mentioned earlier. But their gas components do collide, creating shock waves that can trigger intense bursts of star formation. The gravitational tides during a merger can fling stars into extended tidal tails, stretching hundreds of thousands of light-years into space. Some of these stars end up in the vast empty regions between galaxies, wandering the intergalactic void far from any galactic disk. The Milky Way itself shows evidence of past mergers. Gaia data has revealed multiple stellar streams, the remnants of smaller galaxies and globular clusters torn apart by our galaxy's tidal forces. The Sagittarius dwarf elliptical galaxy is currently merging with the Milky Way, stretched into long streams that wrap around our galaxy. Studies published in 2020 and 2021 identified another ancient merger, with a galaxy called Gaia Enceladus, or the Kraken, that occurred about 10 billion years ago. This merger may have significantly shaped the Milky Way's structure, helping to build up the thick disk and stellar halo. These merger remnants populate the emptiest regions of the galaxy. The stellar halo, that roughly spherical distribution of old stars surrounding the disk, has a density so low that calling it empty would be generous. At 50,000 light-years from the galactic center, in the depths of the halo, you might find only one star per 10,000 cubic light-years. A planet in such a region would have a night sky unlike anything we can experience from Earth. The Milky Way's disk would appear edge-on as a faint band of light across the sky, but there would be no nearby stars, no bright constellations, just the distant glow of the galaxy seen from outside. The distribution of galaxies in the universe also reflects this fundamental emptiness. Galaxies themselves are not uniformly distributed, but cluster together in groups and clusters, connected by filaments in a vast cosmic web. Between these filaments lie voids, regions hundreds of millions of light-years across containing very few galaxies. The largest known void, the Bootes void discovered in 1987, spans about 330 million light-years. Within this region, galaxy density drops to roughly 10% of the universal average. The emptiness of individual galaxies is nested within the larger-scale emptiness of cosmic voids. This hierarchical structure, with emptiness on multiple scales, emerges naturally from the initial density fluctuations after the Big Bang. Computer simulations of cosmic structure formation, which follow the evolution of billions of dark matter particles from shortly after the Big Bang to the present, reproduce the observed cosmic web structure remarkably well. Dense regions attract more matter and grow denser, while underdense regions lose matter and become voids. The same physics that makes individual galaxies mostly empty also creates the vast voids of the cosmic web. Theories of galaxy formation predict that the first galaxies were smaller and denser than modern galaxies like the Milky Way. These early galaxies formed from the densest regions of the universe when it was younger and more compact. Over billions of years, galaxies grew through two main processes: accretion of gas from their surroundings and mergers with other galaxies. As galaxies grew larger, they generally became less dense overall, though their central regions might remain compact. This inside-out growth, where the central regions form first and the outer disk builds up gradually over time, is supported by observations showing that stars in the outer Milky Way are generally younger than stars in the inner regions. The paper published in Nature Astronomy in June 2024 confirmed this picture for the Milky Way. By measuring stellar ages across the galaxy, researchers traced the size evolution over time. They found that the Milky Way's half-light radius has grown from about 2 kiloparsecs when the universe was 4 billion years old to 5.75 kiloparsecs today. This growth occurred as the galaxy accreted gas and formed new stars preferentially in the outer disk, gradually expanding its size while the space between stars remained vast. Comparing the Milky Way's size evolution to that of distant galaxies observed at different cosmic times shows that our galaxy followed a similar growth pattern to other disk galaxies of comparable mass. High redshift surveys with the Hubble Space Telescope and now the James Webb Space Telescope have measured galaxy sizes when the universe was much younger. These measurements show that galaxies at high redshift are typically more compact than local galaxies of the same mass. As the universe aged and galaxies grew, they expanded, increasing the already substantial emptiness between their stars. The angular momentum of the gas from which galaxies form plays a fundamental role in determining their final size and structure. Gas with more angular momentum spreads out into a larger disk when it collapses, while gas with less angular momentum forms a more compact system. The amount of angular momentum is set by tidal interactions during the early stages of structure formation, when the proto-galactic cloud was still part of the larger-scale density field. These early conditions, determined by quantum fluctuations during cosmic inflation, thus ultimately influence the emptiness of galaxies billions of years later. One of the most spectacular consequences of galactic emptiness is what happens when galaxies collide. Despite the violence implied by the word collision, the reality is far more subtle and strange. When two galaxies pass through each other, the actual stars almost never physically collide. The emptiness that pervades each galaxy ensures that the stars slip past each other like dancers in an elaborate cosmic ballet, their paths altered by gravity, but their physical integrity preserved. Consider the Andromeda Galaxy, our nearest large galactic neighbor, located approximately 2.5 million light-years away. Andromeda is approaching us at about 110 kilometers per second. In approximately 4 billion years, Andromeda and the Milky Way will begin their first close passage. Computer simulations of this future collision have been run many times, using the known masses, positions, and velocities of both galaxies. These simulations consistently show the same remarkable result. Despite billions of stars from each galaxy interpenetrating, the probability of any two stars actually colliding is essentially zero. To understand why, let's run the numbers. The Milky Way's disk has a diameter of about 100,000 light-years and contains roughly 300 billion stars. Andromeda is somewhat larger, with perhaps 400 billion to 1 trillion stars. When the galaxies collide, all these stars will pass through the same region of space. Yet the cross-sectional area of a star is minuscule compared to the area of the galactic disk. Our Sun has a diameter of about 1.4 million kilometers. Its cross-sectional area is about 1.5 trillion square kilometers. The area of the Milky Way's disk is roughly 7 times 10 to the 36th square meters, or 7 times 10 to the 24 square kilometers. If we distributed 300 billion stars randomly across this area, the fraction of the disk's area covered by stellar surfaces would be about 0.01. That's 1 part in 100 trillion. Now imagine two such disks passing through each other. The chance of any given star from one galaxy hitting any star from the other galaxy is proportional to this tiny fraction. Even accounting for the fact that there are hundreds of billions of opportunities for collision, the total expected number of stellar collisions during the entire merger might be just a few, or possibly zero. This counterintuitive result stems directly from the emptiness we've been exploring. Galaxies are so dominated by empty space that even when you overlap two galaxies completely, the emptiness still prevails. The stars pass through like raindrops falling through a forest, each drop finding a path between the trees. It's only on the very largest scales, where the collective gravitational influence of billions of stars matters, that the collision has dramatic effects. Those gravitational effects, however, are profound. Although individual stars don't collide, the overall mass distribution of each galaxy exerts enormous tidal forces on the other. These forces stretch and distort both galaxies, pulling them into elongated shapes. long tidal tails form, streaming stars and gas hundreds of thousands of light-years into space. The famous antennae galaxies, NGC 4038 and NGC 4039, showcase this process beautifully. Two spiral galaxies in the process of merging have been drawn into elaborate tails resembling an insect's antenna, with stars scattered across a region more than 300,000 light-years across. The Hubble Space Telescope has captured numerous images of colliding galaxies at various stages of the merger process. These images reveal the diversity of structures that can form: bridges of stars connecting two galaxies, rings of young stars surrounding merged cores, bizarre asymmetric shapes that bear no resemblance to the neat spiral or elliptical forms of isolated galaxies. Yet in every case, if you could zoom in to observe individual stars, you'd see them sailing through vast expanses of emptiness, their solitary nature preserved despite the cosmic chaos surrounding them. When galaxies collide, their gas components do experience actual collisions, unlike the stars. Gas clouds from the two galaxies slam into each other at speeds of hundreds of kilometers per second, creating shock waves that heat the gas and compress it. This compression can trigger intense bursts of star formation, converting gas into stars at rates far exceeding those in isolated galaxies. These starburst galaxies, as they're called, can form stars 10 or even 100 times faster than the Milky Way currently does. The increased star formation temporarily increases the stellar density in certain regions, though the overall emptiness of the merger remnant remains overwhelming. The antennae galaxies contain numerous superstar clusters, massive young clusters with millions of stars packed into regions just a few light-years across. These clusters form in the compressed gas where the two galaxies' interstellar media collide. Observations with the Chandra X-ray Observatory have identified hundreds of X-ray sources in the antennae, including young neutron stars and black holes produced by the massive stars born in the starburst. Even these intense star-forming regions, among the most active in the nearby universe, produce stars that will eventually disperse into the emptiness of the merger remnant. The supermassive black holes at the centers of colliding galaxies also interact, though not immediately. Each galaxy typically harbors a black hole with a mass of millions or billions of times the Sun's mass at its core. When the galaxies merge, these black holes begin a slow in-spiral toward each other, sinking toward the center of the merged system through a process called dynamical friction. As the black hole moves through the sea of stars, it gravitationally interacts with them, transferring momentum and gradually losing orbital energy. This in-spiral can take hundreds of millions of years, with the black holes approaching each other while still separated by thousands or even tens of thousands of light-years. Eventually, when they come within a few light-years of each other, gravitational radiation becomes important. The black holes emit gravitational waves, ripples in space-time that carry away energy and angular momentum, causing the orbit to decay further. In the final moments before merger, the black holes spiral together at nearly the speed of light, releasing a tremendous burst of gravitational waves before coalescing into a single, larger black hole. The LIGO and Virgo gravitational wave detectors have observed many black hole mergers, though these involve stellar mass black holes with masses of tens of solar masses rather than the supermassive black holes at galactic centers. Mergers of supermassive black holes produce gravitational waves at lower frequencies that current ground-based detectors cannot observe. The planned Laser Interferometer, Space Antenna or LISA, scheduled for launch in the 2030s, will detect these lower frequency gravitational waves, allowing us to observe supermassive black hole mergers directly. After a galaxy collision, the merger remnant typically relaxes into an elliptical galaxy, a smooth distribution of stars lacking the disk and spiral arms of the progenitor galaxies. This transformation demonstrates another aspect of galactic emptiness, The stellar orbits in elliptical galaxies are randomly oriented rather than organized into a disk. Stars move on elongated elliptical paths that take them through the galaxy at various angles. The resulting distribution still maintains the fundamental emptiness we've been discussing, but with a different geometry. An elliptical galaxy is like a spherical or ellipsoidal cloud of stars, each star on its own independent orbit, all of them separated by vast distances. The Milky Way-Andromeda collision will likely produce an elliptical galaxy that astronomers have whimsically nicknamed Milkomeda. Simulations suggest that after the first passage in about 4 billion years, the two galaxies will swing apart, then fall back together for additional passes. The merger will be complete in perhaps 6 or 7 billion years, by which time the Sun will be nearing the end of its main sequence lifetime. Our solar system will likely survive the merger unscathed, though it might be flung into a different orbit, perhaps ending up in the outer regions of Milkomeda rather than in the middle regions where we are now. For a hypothetical observer on Earth during the collision, if Earth still exists and hasn't been rendered uninhabitable by the Sun's increasing luminosity, the night sky would be spectacular. Andromeda would grow larger in the sky over millions of years, eventually filling a substantial portion of the celestial sphere. During the closest passages, the sky would be ablaze with newly forming stars in compressed gas clouds. Tidal tails would streak across the heavens. Yet despite this celestial drama, the actual risk to our solar system from passing stars would remain minuscule. The emptiness protects us even during galactic collision. Minor mergers, where a small galaxy merges with a much larger one, are even more common than major mergers between comparable galaxies. The Milky Way is currently absorbing several small satellite galaxies. We already mentioned the Sagittarius dwarf elliptical galaxy, which is being tidally disrupted and absorbed. The Canis major dwarf galaxy, if it's indeed a distinct structure and not just a concentration of disk stars, is also in the process of merging with the Milky Way. These minor mergers add stars to our galaxy but have less dramatic effects than major mergers. Gaia has revolutionized our understanding of the Milky Way's merger history. By measuring precise positions and velocities for billions of stars, Gaia allows astronomers to trace stellar orbits backward in time, identifying groups of stars that move together and likely share a common origin. Studies published between 2018 and 2025 have identified numerous stellar streams and kinematic groups associated with ancient merger events. The Gaia-Enceladus merger, which occurred approximately 10 billion years ago, may have brought 100 million to 1 billion stars into the Milky Way, significantly contributing to the stellar halo. These merger remnants are now spread throughout the galaxy, their stars mixed with the native Milky Way population. Yet we can still identify them by their chemical compositions and orbital properties. Stars from Gaia-Enceladus have slightly different abundances of heavy elements compared to stars that formed in the Milky Way's disk. They also tend to orbit on more elongated and inclined paths. The fact that we can still distinguish these populations 10 billion years after the merger testifies to the long, dynamical timescales in galaxies, a consequence of the vast emptiness and the correspondingly weak gravitational interactions between individual stars. Ultra-diffuse galaxies represent an extreme example of galactic emptiness. These enigmatic objects, first recognized as a distinct class in 2015, have sizes comparable to the Milky Way but contain only about 1% as many stars. Their stellar densities are extraordinarily low, making them among the most empty galaxies known. One ultra-diffuse galaxy called Dragonfly 44, located in the Coma cluster, has a stellar mass comparable to a small dwarf galaxy, but is spread across a region 50,000 light-years in diameter. What makes ultra-diffuse galaxies so empty? Several theories have been proposed. Some might be failed, Milky Way-like galaxies that didn't manage to form many stars despite residing in large dark matter halos. Others might have had more normal star formation initially, but then lost most of their stars through tidal stripping when passing through galaxy clusters. Some might have experienced intense supernova feedback early in their history that expelled most of their gas, preventing further star formation. The debate continues, with observations from Hubble and other telescopes providing new clues. The emptiness of galaxies profoundly influences the evolution of stars and planetary systems. When we think about stellar evolution, we typically imagine an isolated star consuming its nuclear fuel over billions of years, eventually dying in a manner determined by its mass. This picture is largely accurate precisely because of galactic emptiness. Stars spend most of their lives far enough from neighbors that gravitational perturbations are negligible, allowing stable, predictable evolution. Our Sun exemplifies this isolated existence. The nearest star, Proxima Centauri, is 4.24 light-years away. At this distance, Proxima's gravitational influence on the Sun is utterly negligible, roughly equivalent to the gravitational pull of a small asteroid within our solar system. This isolation has allowed the Sun to burn hydrogen steadily for the past 4.6 billion years, maintaining the relatively constant luminosity that has kept Earth habitable for most of that time. Had we been born in a denser stellar environment, this stability might not have been possible. Planets form from disks of gas and dust surrounding young stars. These protoplanetary disks are the birthplaces of worlds, regions where dust grains collide and stick together, gradually building up planetesimals, then planets. The process takes millions of years and requires a relatively undisturbed environment. If another star passed too close during this critical period, the gravitational perturbation could disrupt the disk, scattering material or truncating the disk's outer regions. In dense stellar environments, such encounters might be common enough to interfere with planet formation. Studies of planet-forming disks in the Orion Nebula cluster, one of the nearest regions of active star formation at about 1,300 light-years distance, reveal this effect in action. The cluster contains thousands of young stars packed into a region just a few light-years across, much denser than our solar neighborhood. Observations with the Hubble Space Telescope and the Atacama Large Millimeter Array, or ALMA, show that many disks in Orion are smaller than typical isolated disks, likely truncated by gravitational encounters with neighboring stars or by intense ultraviolet radiation from the cluster's hot, massive stars. A paper published in Astronomy and Astrophysics in November 2024 presented ALMA observations of protoplanetary disks in various star-forming regions, finding that disk sizes correlate with stellar density. In denser regions, disks tend to be smaller, suggesting that the environment influences planet formation. Planets that do form in dense clusters may preferentially be smaller or orbit closer to their stars, where the disk material is less vulnerable to external perturbations. This environmental effect might influence the types of planetary systems that form in different galactic locations. Once formed, planetary systems face another challenge in dense environments: gravitational perturbations that could destabilize planetary orbits or strip planets from their stars entirely. Computer simulations of planetary dynamics in clusters show that close stellar encounters can scatter planets onto eccentric orbits or eject them into interstellar space. Some of these ejected planets become free-floating, wandering the galaxy untethered to any star. Microlensing surveys have detected hints of a population of such rogue planets, though the exact number remains uncertain. In our relatively empty galactic neighborhood, these risks are minimal. The probability of another star passing within 100 astronomical units of the Sun, close enough to potentially perturb the outer planet's orbits, is extraordinarily low over the Sun's lifetime. Calculations suggest such encounters occur perhaps once every few billion years. For Earth and the inner planets orbiting much closer to the Sun, where the Sun's gravitational influence dominates, the risk is even lower. Our solar system has likely remained dynamically stable throughout its history, undisturbed by stellar neighbors. The Oort cloud, that hypothetical sphere of icy bodies extending perhaps 50,000 astronomical units from the Sun, is more vulnerable to perturbations. Passing stars can gravitationally jostle Oort cloud objects, occasionally sending comets plunging toward the inner solar system. Some astronomers have speculated that periodic comet showers, possibly correlated with mass extinctions on Earth, might result from stellar encounters disturbing the Oort cloud. However, the evidence for this remains contentious, and the fundamental emptiness of our galactic environment means such encounters are rare regardless. For life to arise and evolve, planetary systems generally need stability over billions of years. Simple, single-celled life appeared on Earth within the first billion years, but complex multicellular life took much longer, not appearing until roughly 600 million years ago. Intelligent life capable of contemplating the cosmos emerged only in the last few million years. This long time scale requires a stable environment. A planet whose orbit is disrupted by a passing star, or which is ejected from its system entirely, would have its biological evolution cut short. The galactic habitable zone is a concept similar to the habitable zone around a star, but applied to the galaxy as a whole. Just as planets need to orbit at the right distance from their star to maintain liquid water on their surfaces, they may also need to be located in the right region of the galaxy to allow life to flourish. Too close to the galactic center and the stellar density increases, raising the frequency of disruptive encounters and exposing planets to higher levels of cosmic radiation from supernovae and the central supermassive black hole. Too far from the center, in the outer reaches of the galactic disk or in the halo, and there may be insufficient heavy elements to form rocky planets. Earth sits comfortably within the Milky Way's habitable zone, about 26,000 light-years from the galactic center. Here, stellar density is low enough that close encounters are rare, but high enough that there's a healthy mix of heavy elements in the interstellar medium from which our solar system formed. The Sun's nearly circular orbit keeps us at roughly the same galactocentric distance, avoiding passages through the more crowded inner galaxy. Our position between major spiral arms places us in a relatively quiet region, where supernova rates are lower than in the star-forming spiral arms themselves. This perspective suggests that the emptiness of galaxies isn't just a curious fact, but a necessary condition for complex life. If galaxies were much denser, with stars separated by light months rather than light years, the constant gravitational perturbations and higher radiation environment might make it difficult for life to develop. The same emptiness that makes space travel daunting may be what makes our existence possible. We live in a universe fine-tuned not just at the level of fundamental physics, but also at the level of galactic structure. Of course, this reasoning involves significant speculation. We have only one example of life, that on Earth, and we don't know how robust biology is to different environmental conditions. Perhaps life is more adaptable than we imagine. Perhaps there are forms of life on rogue planets heated by internal radioactivity or tidal forces, completely independent of stars. Perhaps life could arise in dense stellar environments, adapting to higher radiation levels and more frequent catastrophic events. Our understanding is limited by our sample size of 1. The search for extraterrestrial intelligence, or SETI, implicitly assumes that other technological civilizations exist somewhere in our galaxy. Given the Milky Way's vastness and the hundreds of billions of stars it contains, the reasoning goes, surely we're not alone. Yet the emptiness we've been discussing poses a challenge for SETI. If civilizations are widely separated, communication becomes difficult. Radio signals travel at the speed of light, taking years or centuries to traverse the distances between stars. A conversation with an alien civilization just 10 light-years away would involve 20-year round-trip communication times, making dialogue impractical. The Fermi paradox, named after physicist Enrico Fermi, who reportedly asked, "Where is everybody?" during a lunch discussion in 1950, points out the apparent contradiction between the high probability of extraterrestrial civilizations and the lack of evidence for them. Many proposed solutions to the Fermi paradox relate to the emptiness of space. Perhaps interstellar travel is simply too difficult, the distance is too vast for civilizations to spread throughout the galaxy. Perhaps civilizations exist but are too far apart to detect each other's signals. Perhaps the galaxy is indeed teeming with life, but the emptiness keeps it isolated, each civilization a lonely island in the cosmic ocean. Alternatively, perhaps we're among the first. Stars have been forming in the Milky Way for over 13 billion years, but the earliest generations of stars contained almost no heavy elements. Rocky planets like Earth require carbon, oxygen, silicon, iron, and other elements forged in stellar nucleosynthesis. These elements didn't become abundant in the interstellar medium until multiple generations of stars had lived and died, enriching the gas with their nucleosynthetic products. Perhaps Earth-like planets could only begin forming in significant numbers within the last few billion years, making us part of the first wave of intelligent life in the galaxy. This possibility would resolve the Fermi paradox in a satisfying way. We don't detect other civilizations because they don't exist yet, or have only recently arisen like us. The galaxy's future might see the emergence of many technological civilizations, eventually filling the emptiness with communications and perhaps even physical exploration. From this perspective, we live at a special time in cosmic history, near the beginning of intelligence in the universe. It's a humbling and inspiring thought. The emptiness between stars also affects how we might explore the galaxy in the distant future. Chemical rockets, which carry their propellant with them, are fundamentally limited by the tyranny of the rocket equation. To accelerate a payload to high speeds requires exponentially more propellant. Reaching even a small fraction of light speed with chemical rockets is essentially impossible. Even nuclear propulsion, whether fusion or fission-based, faces severe practical limitations when confronting the vast distances between stars. One proposed solution is the Generation Ship, a massive spacecraft designed to travel for centuries or millennia, supporting multiple generations of crew who would be born, live, and die during the journey. These ships would need to be essentially self-contained ecosystems, providing everything needed for human life indefinitely. The engineering challenges are immense, maintaining ecological stability for thousands of years, providing radiation shielding, preventing social breakdown among the crew, managing the psychological effects of permanent confinement. The emptiness of space means that once you embark on such a journey, there's no turning back and no help if something goes wrong. Light sails offer another approach that takes advantage of the emptiness. A spacecraft with an enormous ultra-thin reflective sail could be accelerated by laser beams from the home system, potentially reaching a significant fraction of light speed without carrying propellant. The Breakthrough Starshot initiative, announced in 2016, proposes sending tiny gram-scale probes to Alpha Centauri using this method, potentially reaching the system in 20 to 30 years after launch. However, scaling this technology to carry human crews remains enormously challenging. Wormholes, hypothetical tunnels through space-time connecting distant regions of the universe appear frequently in science fiction as a way to bypass the emptiness between stars. General relativity allows for wormhole solutions mathematically, but maintaining a traversable wormhole would require exotic matter with negative energy density, something never observed and possibly forbidden by quantum field theory. While we can't rule out the possibility that advanced civilizations might manipulate space-time in ways we don't yet understand, there's currently no evidence that faster-than-light travel or shortcuts through space are possible. The reality is that the emptiness of galaxies may be an insurmountable barrier to physical exploration on galactic scales. Even traveling at 99% of light speed, crossing the Milky Way would take over 100,000 years. Building an infrastructure to support such journeys seems barely imaginable with current or foreseeable technology. The galaxy may forever remain mostly inaccessible to us, known only through the light that reaches our telescopes after traveling for centuries or millennia across the void.